Assalamualaikum and hi everyone. In this lesson, we will learn about quantization of light. This chapter is actually the opening of one great revolutionary in science that shook the whole world in the early part of 20th century, where classical physics known as Newtonian physics is distinguished from the modern physics. Before we begin, for those who enroll in SP025 course, you should know that there will be 5 marks allocated for this chapter in our final PSPM2. Alright, let's look at the content of this chapter. This chapter has only two subtopics. They are Planck's quantum theory and photoelectric effect. As what we have learned in the previous chapter, physical optics, the wave theory of light is strongly supported by the observation that light exhibits interference and diffraction. Wave theory also explains the refraction of light and the fact that light travels more slowly in denser medium like water and glass than it does in air. Last semester, we learned that there is conservation of energy and that the energy can be carried from place to place by particles or by wave. Generally, we also note that light carries energy and is obvious to anyone who has focused the sun's light rays with a magnifying glass on a piece of paper and burned a hole in it. So how does the light carries the energy? For one thing, light does not reveal itself in any obvious way as being made up of tiny particles, nor do we see light wave passing by as do light water wave with our visible eyes. Later, before the end of 19th century, light was considered to be an electromagnetic wave, also known as EM wave in electromagnetic radiation. It was Maxwell who formulated the classical theory of electromagnetic radiation, bringing together, for the first time, electricity, magnetism, and light as different manifestations of the same phenomenon. As progress in the science field was happening, Maxwell's suggestion about the wave nature of electromagnetic radiation was helpful in explaining the phenomena such as interference, diffraction, etc. However, he failed to explain various other observations such as the nature of emission of radiation from hot bodies, photoelectric effect, as in ejection of electrons from a metal compound when electromagnetic radiation strikes on it, the dependence of heat capacity of solids upon temperature, line spectra of atoms, especially hydrogens. One of the observations that was unexplained at the end of 19th century was the spectrum of light emitted by the hot objects. Solids, when heated, emit radiation varying over a wide range of wavelengths. As for example, when we heat a solid object, color changes continue with a further increase in temperature. This change in color happens from a lower frequency region to a higher frequency region as the temperature increases. For example, in many cases, it changes from red to blue. An ideal body which can emit and absorb radiation of all frequencies is called a blackbody. The electromagnetic radiation emitted by such bodies is called blackbody radiation. From the blackbody experiment, the distribution of energy in blackbody E depends only on the temperature due to this expression. E is equal to kBT, where kB is Boltzmann constant, which is equals to 1.38 times 10 power of negative 23 joule per Kelvin. And the temperature is measured in Kelvin. Thus, from the expression itself, we can see that energy is directly proportional to the temperature. This graph shows the comparison of the Wien's and the Rayleigh-jeans theories to that of the experimental result on the spectrum of EM radiation emitted by the blackbody. Wien's theory was accurate at short wavelengths, but deviated from experiment at longer wavelengths, whereas the reverse was true for the Rayleigh-jeans theory. At a given temperature, The intensity of radiation is found to increase with an increase in the wavelength of radiation, which increases to a maximum value and then decreases with an increase in the wavelength. This phenomenon couldn't be explained with the help of Maxwell's suggestions. Hence, Planck proposed Planck's quantum theory to explain this phenomenon. Once Planck proposed an empirical formula that nicely fit the data, he sought a theoretical basis for the formula, and later he came with a few assumptions. Planck's assumptions suggest that EM radiation emitted by the blackbody is in discrete or separate packets of energy. Each packet is called a quantum of energy. This means the energy of EM radiation is quantized. He also made an assumption that the energy size of the radiation depends on its frequency. A simple analogy may help. Given that we have a ramp and a staircase, in both situations, the balls lost the potential energy, but in different ways. For the past few chapters, we expressed the unit of energy in joules, but in this chapter, it is convenient to express many quantum energies in electron volts or EV. The electron volt is a unit of energy that can be defined as the kinetic energy gained by an electron in being accelerated by a potential difference of 1 volt. In 1905, the same year that he introduced his famous special theory of relativity, Albert Einstein made a bold extension of Planck's idea by proposing that electromagnetic radiation is also quantized. It consists of particle-like packets, bundles of energy, which called photons of electromagnetic radiation. For EM radiation of n packets, the energy En is given by En is equals to NHF, where n real number 1, 2, 3. NH is Planck constant, which is 6.63 times 10 power of negative 34 joule second. Since all light ultimately comes from a radiating source, this suggests that perhaps light is transmitted as tiny particles, or photons, as they are now called, rather than as a wave. By definition, photon is a particle with zero mass consisting of a quantum of electromagnetic radiation where its energy is concentrated. A photon may also be regarded as a unit of energy equals to HF. Photons travels at the speed of light in a vacuum. They are required to explain the photoelectric effect and the other phenomena that require light to have particle property. As you can see, the table shows the differences between the photon and the EM wave. To prove his proposal, Einstein proposed a test of the quantum theory of light, quantitative measurements on the photoelectric effect. The photoelectric effect is the phenomenon that when light shines on a certain metallic surface, causes the emission of electrons from the surface. This figure shows the emission of the electron from the surface of the metal after shining by the light. This emission of electrons is called photoelectrons. In the photoelectric experiment, a metallic plate E is connected to the negative power supply, work as cathode. Then, we have another plate connected to the positive power supply as its anode. The two plates are encased in an evacuated vacuum tube, and they are connected to a voltmeter, galvanometer, and rheostat. No current is recorded across the galvanometer for the time being, until a monochromatic light with certain wavelength and intensity is incident or hits the plate E, which is the cathode. Electrons start to emit from the metal surface and accelerated towards plate C. These photoelectrons are attracted to the anode and give rise to the photoelectric current, which is detected by the galvanometer. When the positive voltage or the potential difference across the cathode and anode is increased, more photoelectrons reach the anode. Thus, the photoelectric current increases. As positive voltage becomes sufficiently large, the photoelectric current increases until it reaches a maximum constant value called saturation current, noted as Im. By definition, we can say that this saturated current is the maximum constant value of photoelectric current when all the photoelectrons have reached the anode. If the positive voltage is gradually decreased, the photoelectric current also decreases slowly. Even at zero voltage, there are still some photoelectrons with sufficient energy reach the anode and the photoelectric current flows is I naught. Finally, when we reverse the power supply terminal, the photoelectric current decreases even further to very low values, since most photoelectrons are now repelled by the anode, which is now has negative potential. As the potential of the anode becomes more negative, less photoelectrons reach the anode. And thus, the photoelectric current drops until its value equals 0, which the electric potential at this moment is called the stopping potential or stopping voltage, Vs. If you still remember, saturation current is a maximum value of photocurrent when all the photoelectrons reach the anode. So, for stopping potential, it refers to the minimum value of negative voltage when there are no photoelectrons reaching the anode. From this graph, the saturation current is located over here, where the current is at the maximum and the stopping voltage is at the end here, as there are no more current detected through the galvanometer. You should know that the potential energy, U, due to this stopping voltage now equals the maximum kinetic energy of the photoelectron, or by formula, U, which is the EVS, is equal to half mv square of the maximum of the photoelectron. The variation of photoelectric current I as a function of the voltage V can be shown through this graph here. As you can see, the photoelectric effect that we discussed just now progressed from the right to the left of this graph. The portion of the graph on the right was collected before reversing the terminal of the power supply, and after we reverse, the photoelectric current is 0 until it reaches certain voltage known to us as stopping voltage. From what have been explained by Einstein on photoelectric effect, EM wave can be considered as stream of photons. A photon itself is a packet of electromagnetic radiation with particle-like characteristics and carries the energy given by E equals to hf and hc over lambda. Whenever EM wave shines on a surface, especially metal, which we know has tons of free electrons on its surface, these photons of this EM wave are used to break the electron bonding and accelerates the emitted electron from the surface of cathode to anode, as we experience in photoelectric effect experiment. To further understand on how the photoelectrons emission happen, might as well we take a look on a few terms to explain this phenomena. The first one is work function. It is the minimum energy of EM radiation required to emit an electron from the surface of the metal. The value depends on the element of the metal being used. As for example, aluminium has work function of 4.3 electron volt and gold has 5.1 electron volt. Its formula is W0 equals to E minimum, and when E is at minimum, it is due to HF0. Therefore, W0 is HF0. We will discuss on F0 shortly after this. So, Einstein photoelectric equation is given by E equals to K maximum plus the work function, which is W0. From the formula, take note that the E is the energy carried by the photons, which is HF. Meanwhile, the K maximum is the equals to half mv square to EVS equals to HF minus HF0, which later refer to maximum kinetic energy of the photoelectron emission. Next is the threshold frequency, noted as F0, which defined as minimum frequency of EM radiation required to emit an electron from the surface, and threshold wavelength, defined as maximum wavelength of EM radiation required to emit an electron from the surface of the metal. Okay, now we look at all the cases or situation whenever an EM radiation shines onto a metallic surface. Remember that photon is a packet energy in EM radiation. In this first case, if electron receive photon energy more than the work function of that metal, therefore, the electron has enough energy to overcome the binding force and the extra would appear as the maximum kinetic energy gained by the photoelectron. From Einstein photoelectric equation, E is equals to W naught plus K maximum. This case is possible since the energy of the photon, which is HF, is greater than the work function, W naught. Or we can also see this situation when the frequency is greater than the threshold frequency. For the second case, if the photon energy is the same as the work function of the metal, where the energy received by the electrons only enough to liberate it, the electron emission still occur, but maximum kinetic energy is somewhat zero. We can also refer this situation as the frequency is equal to the threshold frequency. Lastly, if the electron receives photon energy less than its work function, no photoelectron emission, since there is not enough energy even to liberate it. This situation is the same as the frequency is less than that of its threshold frequency. Let us now see what will happen if we use EM radiations with different intensity but with fixed frequency. Let's say we have two EM radiations where one intensity is double than the other one. A linear line in current against intensity graph shows that the current for double intensity would also increase twice as much than the other one. As for intensity against voltage graph, even though the radiation intensity is double, they only resulted to twice as much of saturation current level, but ended up with the same value of stopping voltage. So we can conclude that the photoelectric current is directly proportional to the intensity of the radiation. So how about the radiation of different frequencies but its intensity is fixed? Since they have different values of frequency, so we expect them to have different value of stopping voltage. The one with low frequency has lower stopping voltage. And if the stopping voltage is zero, that means it resonates on the threshold frequency. If we use different metals of cathode but the intensity and frequency of the radiations are fixed, we should know that the only difference is work functions values. They will have the same saturation current level, but the one with higher work function has higher magnitude of stopping potential. As we can see in this figure, the graph shows the variation of stopping voltage with frequency. They are ordered in that manner. We are almost towards the end of this chapter. I know that this chapter is quite boring and dull, and any other words that mean the same, but bear with me. This chapter is actually the opening of one great revolutionary in science that shook the whole world in the early part of 20th century, where classical physics, known as Newtonian physics, is distinguished from the modern physics. Experimental observations deviate from classical predictions based on wave theory of light. Hence, the classical physics cannot explain the phenomenon of photoelectric effect. The modern theory, based on Einstein's photon theory of light, can explain the phenomenon of photoelectric effect. It is because Einstein postulated that light is quantized and light is emitted, transmitted, and reabsorbed as photons. Led by the assumption made by Planck, perfected beyond our minds by the great Albert Einstein, who also the person behind the special theory of relativity, then with the theory of quantum mechanics of Schrödinger and Heisenberg, which has been so effective in explaining the structure of matter. So, that's the end of this chapter. Thanks for watching. Don't forget to subscribe, like, and promote our DC Physics KMPk channel. Assalamualaikum and bye-bye.